Example 4 says a note will pay $50,000 at maturity 5 years from now. How much should you be willing to pay for the note now if the money is worth 6.4% compounded continuously? So, again, we are compounded continuously, so we know we're going to use the formula A is equal to PE raised to the RT. So it says a note will pay $50,000 at maturity, so that means that A is equal to $50,000. 5 years from now means that T is equal to 5. And then it says, how much should you be willing to pay for the note now, which means we are looking for P. So plugging in what we know, 50,000 is equal to P is the unknown, E raised to the R, and R we forgot to label is 6.4%. So R is equal to 6.4%, which as a decimal, again we move the decimal place over to the left 2 units, and that would be 0.064. So R is 0.064 and T was 5. This is not an exponential equation. Again, it's not an exponential equation because the variable does not lie in the exponent position. The variable is P and it's not an exponent. So what we need to do here is just solve for P. P is currently being multiplied by E raised to the 0.064 times 5. So in order to solve for P, we just need to divide both sides by E raised to the 0.064 times 5. Using a calculator, we would have 50,000 divided by E raised to the 0.064 times 5. We hit enter and we get $36,307.45. So P is going to equal $36,307.45. So the amount of money that I need to be able to put down today for my note to mature to $50,000 in 5 years at a rate of 6.4% is $36,307.45. Let's take a look at example 5. Example 5 says that a woman invests $5,000 into an account that earns 8.8% compounded continuously. Okay, compounded continuously, so we know that's A equals P E raised to the RT. So she invests $5,000, so we know that P is equal to 5,000. And the percent on that is 8.8%. So R is equal to 8.8%, which again we know is 0.088. And it says she also will invest $7,000 in an account that earns 9.6% compounded annually. So we're going to use our compound interest formula for that. And our compound interest formula says that A is equal to P times 1 plus R over M raised to the M times T. So let's see what it says. Again, it's $7,000, which means P is equal to 7,000. In an account that earns 9.6%, so R is equal to 0.096 or 9.6%. And then we need to figure out how many times a year it's compounded. It's compounded annually, so the M is equal to 1 because annually means once a year. Okay, so now it says use graphical approximation methods to determine how long it's going to take for her total investment in the 2 accounts to grow to $20,000. So what they're trying to figure out is if you have from this formula 5,000 E raised to the 0.088t, and you add that to, from this formula, 7,000 times 1 plus 0.096 over 1 raised to the 1 times t. When is that going to equal $20,000? So if we take the investment we're getting from the one that's compounded continuously and the investment we're getting from the one that's just using compound interest, when is the sum of those two going to equal $20,000? How long do we need to wait? So we need to solve for t. Well, the easiest thing to do before we actually do anything else is just to make this equation a tad bit simpler. Notice that all three of these numbers are divisible by 1,000. So we're just going to start by dividing everything by 1,000 just so that our numbers are a little smaller. So when we're putting them into the calculator, everything doesn't get so large. Now 0.96 over 1 is just going to be 0.96, and 1 times t is just t, equals 20. So now I'm going to put this into a calculator, and what I'm looking for is the point of intersection. I'm trying to figure out, when does this equation intersect this equation? Because the value of the intersection, the x value of that intersection, is going to tell me what t is. So we're going to look for the point of intersection between these two graphs. So let's grab our graphing calculator. In our y equals, for the first one, I'm going to write 5 times e raised to the 0.088, and I'm going to use x instead of t, plus 7 parentheses 1 plus 0.096. That should say 0.096. It should be 0.096. I apologize. So 1 plus 0.096 raised to the x. So that's my first equation. So 5 e to the 0.088x plus 7 parentheses 1 plus 0.096 raised to the x. And my other equation I'm going to write in is this 20 right here. So I'm just going to write in the number 20. Okay, if I hit graph right now, nothing's really going to show up too much because of the fact that our numbers are just going to be off. So what we're going to do right now is change our window so that we can actually find our points of intersection. So we know that time can't be negative, so we're going to make this 0. And hopefully it's going to happen in 10 years, so we're going to leave that as is. We don't care about the minimum value being anything lower than 0. And since we're trying to intersect at 20, we're going to make our y max be 25 so that we have a better idea there. So this is the graph of our exponential function. And then we have our 20. So what we're looking for is this point of intersection. Where do those two intersect? At what point do those two intersect? Well, to find the point of intersection, again, you hit second and then trace for calculate, and you're going to calculate an intersection, so you press the number 5. You want to scroll over to where you think they intersect. So I think it's about here. And you hit enter, and then you hit enter for the other curve, and then enter for your guess. And the calculator tells us that it looks like it's going to be in about 5.6, and then we'll round up. So t is going to be approximately 5.65 years. So in about 5.65 years, the two investments in her accounts are going to grow to $20,000. All right, let's look at number 6. Before we look at the actual question, which is right here, just a couple of things to note. So there's a mathematical model for decay, and it's the same thing for growth as well. It's Q is equal to Q naught. Q sub 0 is called Q naught. E to the RT, so that should look a lot like A equals P e to the RT, where Q naught is the initial amount of your substance at time 0. So Q naught is the initial amount of your substance at time 0. R is the continuously compounded rate of decay, or growth if this were growth. T is time in years, and Q is the amount of the substance at time t. So let's go ahead and try to answer number 6 now. Number 6 says, if the continuous compound rate of decay of carbon-14 per year is R equals negative 0.0001238, how long will it take a certain amount of carbon-14 to decay to half the original amount? So how long lets us know that we're looking for t. So t is going to equal question mark. And again, we have Q is equal to Q naught e to the RT. We know R is our rate. It's given as negative 0.0001238. And we're trying to figure out how long it's going to take for it to be half the original amount. So if we say that Q naught is equal to 1, half of 1 is a half. Half of 1 is a half. So we're going to say that Q is equal to a half. So plugging this in, we'd have 1 half is equal to 1 E. Our rate is negative 0.00012338, and our time is what we're looking for. Now, do I really need this 1 here? No, because 1 times anything is itself. So I'm just going to write this as 1 half is equal to e to the negative 0.00012338t. Well, this is an exponential equation because the variable is in the exponent location. So in order to solve this, we know we need to take the natural log of both sides. So I'm going to take the natural log of the left and the natural log of the right. So it's the natural log of 1 half is equal to the natural log of e raised to the negative 0.0001238t. Well, here again, we know that we use our power to product property for laws of logarithms that says that this guy comes out in front and natural log of e and cancel. So natural log of a half is equal to negative 0.0001238t. We solve for t by dividing both sides by that negative 0.0001238. And then t is going to be approximately, and again we're going to do this in a calculator, the natural log of a half divided by negative 0.0001238 is equal to 5,500, and let's round to the nearest year here, so 5,599 years. So how long will it take a certain amount of carbon-14 to decay to half the original amount? About 5,599 years. That's it for section 3.1.